Today we're going to finish up chapter 23, doing sections 8 and 9 of Gauss's Law. We're going to discuss Gauss's Law with an infinite sheet and also a sphere. Okay, so the figure shows that a portion of a thin, infinite, non-conducting sheet with uniform positive surface charge density sigma. A sheet of thin plastic wrap uniformly charged on one side can serve as a simple model. So right here we have this thin sheet, and it's only charged on one side, as you can see here in the side view. So we need to find the electric field a distance r in front of the sheet. It turns out that a useful Gaussian surface is a closed cylinder, as we used before, with the end caps of area A arranged to pierce the sheet perpendicularly as shown. So it's going right through the center of the sheet. So from symmetry, E must be perpendicular to the sheet, hence the end caps, right? So this is an infinite sheet. It goes on in all directions. So the electric field coming out of this sheet is just going to be straight across, as you can see here. So it's coming out of one side, coming out of the other. Now, since the charge is positive, E is directed away from the sheet. There's going to be no flux through this portion, right, which is the cylinder. So there's not going to be any flux through that. The only flux we're going to have is through the end caps. Okay, so E dot dA is simply E dA. Okay, because they're in the same direction when they're dotted together, right? E is to the right, A is to the right. When you take the dot product, cosine theta is 0. Excuse me, theta is 0, so the cosine of 0 is 1. Okay, so we're just going to use the equation that we have been using, relating the flux to the enclosed charge, or Gauss's law, and the integral of EDA is just going to be the contributions of the flux from both end caps. All right, so EA is going to be from one, and then EA from the other, right? Because if you look, you have EA going in this direction, EA going in this direction. So when you add them together, you're just going to end up with this equation here. So if you take these two A's, two EA's rather, it's just EA plus EA is equal to sigma times A, which is, again, just the enclosed charge, because sigma is the enclosed charge divided by the area. So rearranging for, to solve that for Q, you get sigma times A. And when you add these two together, you get 2EA times epsilon naught is equal to sigma A. The A's are going to cancel out, so we're just going to solve the rest of this for the electric field, and that gets us sigma over 2 epsilon naught, which is the result that they have here. So that's the electric field due to an infinite sheet of charge. Okay, so if you have two conducting plates, it's going to look a little bit differently. All right, so the figure shows that a cross-section of a thin, infinite conducting plate with excess positive charge. The thin plate, the plate is thin and very large, and essentially all the excess charge is on the two large faces of the plate. So how this differs from the previous example is all this excess charge is now on both sides of the plate because it's a conductor, and it's going to be evenly distributed. All right, so if there's no external electric field to force the positive charge into some particular distribution, it's going to spread out all over the two faces with a uniform surface charge density of sigma 1. So just outside the plate, this charge sets up an electric field of magnitude E is equal to sigma 1 over epsilon naught. All right, so that's just for one of the plates. So the other plate shows identical plate, but it now has excess negative charge, having the same magnitude of surface charge density. So the electric field is directed towards the plate, as you can see shown here. Now, if you arrange these plates so that they're close to each other and parallel, the excess charge on one plate attracts the excess charge on the other plate. So you had all of this excess charge over here, and all this excess charge over here is now going to redistribute itself because it's a conductor, and it wants to attract. So you get all the excess charge is now on one side of the plate. Okay. So now they're on the inner faces of the plate. So with twice as much charge now on the inner face of the plate, the new surface charge density, we're just going to call sigma instead of sigma 1, on each interface is going to be twice that of sigma 1. All right, so thus the electric field at any point between the plates has the magnitude. All right, so this was our original sigma, and we had 2 of it. Our new sigma for the plate is going to be sigma over epsilon naught. Now this arrangement here is going to be, in later chapters, what we call a capacitor. Just a little heads up for later. Okay, so let's do an example. All right, so the figure down here at the bottom shows portions of 2 large parallel non-conducting sheets. All right, so this is a little bit different. These are non-conducting sheets, so all the charge is going to be fixed, each with a fixed uniform charge on one side. So again, the charge is just on one side. The magnitudes of the surface charge densities are given, so you have sigma of the positive surface charge density of 6.8 microcoulombs per meter squared for the positively charged sheet. Okay, and then for the negatively charged sheet, sigma is going to be 4.3 microcoulombs per meter squared. All right, so find the electric field E to the left of the sheets, between the sheets, and to the right of the sheets. All right, so we're trying to find the electric field here, here, and here, to the left, in the middle, and to the right. Okay, well, with the charges fixed in place, there's because they're non-conductors, we can find the electric field of the sheets by finding the field of each sheet as if it were isolated, and then algebraically adding the fields of the isolated sheets via the superposition principle. We can add the fields algebraically because they're parallel to one another, right? So, all right, so at any point, the electric field E, due to the positive plate, is directed away from the sheet. All right, so we get our electric field. Positive is going to be just the equation that we saw before. Epsilon naught is equal to 6.8, which is our charge density, our area charge density, divided by 2 times epsilon naught, which is 8.85, times 10 to the negative 12, Coulomb squared over Newton meter squared. Okay, and that gets us a result of 3.84 times 10 to the 5th newtons per coulomb. Now, similarly, at any point, the electric field due to the negative plate is directed inward or toward the plate. Okay, so using the same equation, our electric field of the negative plate is just our surface charge density divided by 2 times epsilon naught. So plugging in the values for that, we have 4.3 times 10 to the negative 6 coulombs per meter squared, divided by 2 times epsilon naught, which is 8.85 times 10 to the 12th Coulomb squared over Newton meter squared. Okay, and as a result, this is the negative one, you get 2.43 times 10 to the 5th newtons per coulomb as our electric field. Okay, so the middle picture here shows that the field sets up by the sheet to the left and between and then to the right. So if you look at the top, the positive sheet is going to have this contribution, the negative sheet is going to have this contribution. right? It's going away from the positive towards the negative sheet. All right, so the resultant of these three regions just follow from the superposition principle, which just means we're adding everything together. So to the left, the field magnitude is going to be just R2 subtracted, right? Because if you look to the left, you have one going to the left, one going to the right, so you know the magnitudes must be subtracted. All right, so if we go ahead and subtract them, oops, it's going to be a positive minus our negative. So it's 3.84 times 10 to the negative fifth, whoops, minus 2.43 times 10 to the negative fifth. All right, so the electric field to the left is going to be 1.4 times 10 to the fifth newtons per coulomb, and this is to the left. Okay. All right, so because the E plus is larger than E minus, the net electric field is to the left. So to the right of the sheets, the electric field is going to have the same magnitude, but is directed to the right instead. So if you look over here, you know E is a little bit bigger, E plus is a little bit bigger than E minus, so you're going to have the electric field over here to the right with the same magnitude shown up there. Now between the sheets, the two fields are going to add together because you have going away from the positive and going towards the negative. Two fields will add together. So here you're just going to add them together. You have one of the fields plus the other field is equal to 6.3 times 10 to the fifth newtons per coulomb. And again, the electric field is directed to the right. So if I move my head out of the way here, you can see that the direction of the electric fields for each region. Okay. All right, so then to conclude, we'll just briefly talk about the spherical symmetry. So a shell of uniform charge attracts or repels a charged particle that is outside the shell as if all the shell's charge were concentrated at the center of the shell. So again, a shell of uniform charge, if it has uniform charge, it attracts or repels a charged particle that's outside the shell as if all the shell's charge were concentrated at the center of the shell. So if a charged particle is located inside a shell of uniform charge, there's going to be no electrostatic force on the particle. All right, so think about that. If you have some charge on the inside, you're going to have contribution from all of these. It's going to be a little bit larger here, but you're going to have more of it in this direction. So really, all the charge is just going to, all the force is going to cancel out. All the components will cancel out, no matter where you are inside of a charged shell. Now, if you're outside, let's say over here, all of the charge or all the force on it is going to act as if it were concentrated right here in the center. So if you can you can see that all of the components are really going to cancel. All the like anti-parallel, perpendicular components are going to cancel out when looking at it, and then all the components that are parallel are just going to add together. So it's just going to be like if all of the charge is concentrated at the center. Okay, so then the equations for the electric field is simply just going to be our equation for electric field, which is E is equal to 1 over 4 pi epsilon naught, or K, times Q divided by R squared. That's the electric field as if you had all the charge at the center. That's for when you're looking at something that is past or outside of the shell. If you're looking for something inside the shell, you're just going to have your electric field to be 0, like we just said. Okay. Now, what if you had what if you had an evenly distributed amount of charge, and we'll call that charge Q naught, or Q prime, and then we had a Gaussian surface near the edge. So the dot represents a spherically symmetric distribution of charge of radius r. All right, so this is the full radius of the distribution of charge. whose volume charge density is given by rho and is a function only of the distance from the center. All right, so it's not evenly distributed, but it is symmetrically distributed. So the charged object is not a conductor, and therefore the charge is assumed to be fixed. All right, so not a conductor, all the charge is fixed, means it's not moving. A concentric spherical Gaussian surface that with r is greater than r is shown. Okay, so if we want to look at the spherical distribution then of this, the electric field is just going to be whatever this, and this is for when our radius is inside of the circle, it's just going to be q prime, which is the enclosed charge, divided by r squared. So really this is just the equation we have for an, electric field. Now if the charge was uniform, if you had uniform charge and the field was less than r, then you're going to end up with this result. All right, that's it for the chapter. We'll see you next time.